Hello and welcome to the third episode of Carbon Lab, the podcast where we are talking about materials and polymers. And this is the last episode that we planned out in advance. First, we discussed the history of them and how they came to be. After that, we talked about why they are so great and why they are not so great. And this time we want to talk about what we can do about polymers and our materials in general in the future to make them more sustainable. And as always, I'm here with Dr. Oliver Gould. Oliver has spent the last 15 years leading scientific research and has published over 35 scientific papers and patents. At Made of Air, Oliver leads the R&D department as head of research and innovation.
And I'm joined by, I'm very pleased to say, Barnabas, our brand and marketing manager at Made of Air. He's an ex-journalist and marketing professional, as you know, and he helps startups and established brands to tell their stories. Most importantly for this podcast, he's also a textbook nerd and science enthusiast, I hear.
That still sounds right. And let's roll the intro. So in this episode, we want to talk about what to do with our materials and polymers and how to make them more sustainable in the future. But I guess to get to that future, we first have to talk about our present, right? So what's wrong with our materials today? Why don't we make them sustainable?
So a large part of the problem, as I see it, is about how the plasticky sausage gets made.
Ew. That's a horrible picture.
And that's to say that largely plastics and other materials in general are made in a certain way, which is by large-scale sort of mega facilities that largely benefit from economies of unit scale. And that means that broadly as a society, we've moved our manufacturing and production capabilities to these very large centralized units. And why we do that is, again, because economies of scale, because we can make things cheaper and more efficiently if we do it in these centralized units. But there are problems with that. And the problems with that are largely that it requires a huge amount of investment and significant amounts of financial risk to make these really large-scale, higher capital cost facilities. And the problem with that is that when you have a large amount of infrastructure or material production geared around a certain way of manufacturing things, if you find out that there are problems with those things, or if you need change, as we face as a society with climate change and other things, it's very difficult to pivot. Because what eventually happens is that you have a smaller number and less diverse group of technology players who can afford that cost of entry, who can build these mega facilities, these very centralized units. And what that does is then mean that what we have as a society is much slower innovation and much slower adoption of novel technologies, and a much slower response to market drivers and other geopolitical, socioeconomic things like climate change. So what we see at the moment is that environmental, geopolitical, and economic factors are reshaping our view of global energy and manufacturing demands. But to address these challenges, we need really a shift away from our current model of industrial chemical manufacturing that plastics sort of is symptomatic of.
What you're saying is that, put it very simply, I spent $1 billion on this facility and I'm not going to give it up as long as I don't make a profit. And then it's very hard to change that facility because it was so expensive.
Yes, exactly. And what specifically we need really is the innovation that lots of people are looking to, or the new sort of generation of materials, is an increasing role of bio in our materials, our synthetic materials, to address some of those sustainability challenges. And our ability to incorporate biomaterials or to develop new ones or to make technology is limited by our traditional manufacturing methods.
The real price of manufacturing, namely the effect that certain things and techniques and materials have on the climate and the earth, is not really reflected in the sales price or the final price of the product we buy. Do you think the two are connected?
Yeah, I don't know. I guess the question is a little bit above what I'm necessarily comfortable responding to, but a lot of it comes down to how we've sourced our materials. So synthetic materials broadly have come out of fossil fuels, for better or for worse, in the 20th century. And the way that we generally source fossil fuels leads itself quite well to centralized manufacturing facilities. So just as like maybe a bit of a recap at this point, we talked a lot about how, for a lot of human history, we have relied on natural materials.
Yeah.
And largely we pivoted away from naturally sourced materials at times of deficiency or at times of scarcity.
Yeah.
Like the Second World War, some other times where we suddenly couldn't buy natural materials, or we found it much harder to source them. And, a lot of smart chemists came along and material scientists and came up with basically synthetic materials which utilized broadly waste materials or things that weren't particularly valuable to make something that we could substitute natural materials for. So we talked about synthetic ivory, synthetic, all kinds of things. And that's really where polymers came from. But increasingly what's happened is that we have been able to exploit synthetic materials at such scale without necessarily thinking about the sustainability or the broader ramifications for us as a society, that increasingly people are looking to go back to more natural materials or to slightly change the way we source the raw ingredients to make the things we rely on in daily life.
Just a quick question here, because I think it's important and a lot of people know that already, but not everyone. Why is that such a big issue to pump out dinosaur juice from the ground and make materials out of it?
It's fairly well known. We have a huge stock of carbon that's essentially stored under the ground in the form of fossil carbon. So what I mean by that is coal, oil, these things that have come to exist over millennia or very large time periods that represent a very stable and persistent source of carbon. Mm-hmm. What the problem is that if we take that carbon out of the ground and we use it for something, and in some way that carbon finds its way into the atmosphere, as is the case if we burn something as fuel, or if we make a material out of it that then degrades, or we burn it in some way, then what we end up with is an undesirable amount of carbon dioxide in the atmosphere. Yeah. And why that's undesirable is because it causes climatic change. Broadly, if we tamper or change the makeup of the atmosphere of the Earth, then what we see is that the weather patterns, the whole behavior of planet essentially changes.
Yeah. So this is the thing, like in the past, CO2 levels of the atmosphere were around 1,000 ppm. And then a lot of plants came along. They gobbled up a lot of CO2. And now we have what we have now, or pre-industrial era. And those are the plants that now we are getting out of the ground, basically burning them and putting all that CO2 back to the atmosphere, right?
That's exactly it. So, I mean, this is where we come at the biomass stuff from a different angle. The reason that all of that carbon is under the earth is that organisms are very good at turning carbon into a solid, essentially. And specifically, plants are very good at plucking carbon out of the atmosphere, where it's as a gas, and transforming it into a solid material in the form of the plant, or the solid structure that makes up the organism. When those plants die, or when the organisms die in different forms, then that carbon is, in some cases, stored under the ground and undergoes process whereby it ends up as an oil or a coal or a fossil fuel. Why people are so interested in utilizing bio-based materials or different biomass types is that if we as humanity are looking for ways to remove CO2 from the atmosphere, right? Yeah. To combat climate change, we are currently employing or developing lots of different strategies in order to remove that CO2. One of the best ways to do it, or one of the most effective tools we have to remove CO2 from the atmosphere, is by utilizing plants or utilizing biomass. Mm-hmm. Where we have all these organisms that have over millennia evolved in order to very effectively remove CO2 and turn it into a solid, more stable form. So if we were able to utilize plants or other organisms as part of our materials, as part of our day-to-day existence, then we would effectively be incentivizing or finding a way to remove CO2 from the atmosphere. We try very strongly to develop new materials which can utilize biomass and utilize it specifically for carbon storage as part of materials. But I would quite like to talk a little bit about or address some of the confusing terminology around bio-based materials and biomaterials.
Excuse me, class. Class!
If that's okay with you, Barnabas.
I would love to hear about that. And at some point, I might also nitpick about biomaterials, but let's hear what you have to say.
Okay, so I mean, let's address the first thing we've done incorrectly. We've repeatedly used the term biomaterials, which the keen-witted among you will know that that is not entirely correct. So to start with, a biomaterial in its scientific usage is a material that is engineered to interact with biological systems. Mm-hmm. So if you had a hip replacement or some other medical implant device, that's a great...
I do have that.
That's a great example of a biomaterial. But that doesn't necessarily have to be formed from biomass. It doesn't necessarily have to be biodegradable. It doesn't necessarily have to be any of these things. It just has to interact with biological systems in a way that's engineered. So what we're really talking about is things derived from biomass, which I would call bio-based materials. And bio-based materials are substances that are derived from living organisms. So we've taken something that was previously alive, like a plant, and we've transformed it into something else, into a different material, which is then bio-based. If we now include plastics and polymers, things get a little bit more complicated, maybe. So a biopolymer is a polymer that is extracted from biomass. So in the natural world, lots of different forms of organisms make biopolymers. So make a polymeric material completely on their own.
This is the cellulite we were talking about in the first episode, right?
Yeah.
Okay.
A great example, the most abundant biopolymer, I think, is lignin. So in almost all trees, almost all plant matter, there is lignin. And plants produce lignin because it is so good at resisting degradation. So lignin is a key part of what allows plants to resist the attacks of bacteria, fungi, molds, all sorts of things, and makes them a stable, happy plant. So there are also biodegradable materials, and that basically means that they break down in biological environments. That generally means that they're easily hydrolyzable, which means they're attacked by water, and then they break down when they're in contact with water. But as we sort of talked about last time, I think, biodegradability is a little bit complicated and difficult.
Yes, we did. And the main issue was we don't really know where they end up.
Exactly.
And what they become.
Exactly.
That can lead to problems.
And then the third sort of category here is bio-based polymers, which, as you can imagine, are basically normal plastics, or polymeric materials, but instead of being formed from fossil fuels, they're formed from biomass. So, for example, polyethylene, I can make quite readily from biomass. And generally speaking, so in the case of polyethylene, I would take something like sugar or sugar cane, and I would use it to form a monomeric material, like an ethylene, and then I would do the polymerization to make polyethylene.
So then we have bio-based materials already. Everything is fine. The world is saved. We can go home or not yet.
The thing to sort of talk about here really for me is that bio-based obviously does not necessarily mean sustainable, which is important to sort of caveat what we've been talking about.
That's what I was trying to get to.
So obviously there are very, I don't want to say sketchy ways, but not all biomass is good biomass. For example, it's quite easy to quickly displace agricultural crop. For example, if we grew a load of sugarcane to make bio-PE in such a way that displaced land use for agricultural purposes, you may quite quickly get to a situation where you have a higher carbon cost associated with that than you would otherwise.
We were very lucky with the recording last week. John Oliver, who I personally really appreciate, published the story about corn in the US and how they use it for bioethanol. And according to an article that they cited, the GWP of this bioethanol is actually higher than the fossil one. If you combine like land use and water use and everything, it seems like a really good material and a really good solution to using fuel in combustion engines, which is something that we will have to do for a while at least. But in the end of the day, it turns out that it can be even worse than the fossil counterpart, which is such a weird thing, but...
Yeah, totally. I mean, like, again, just to sort of spout random statistics, I also read in the preparation for this recording that, for example, a complete switch of the 170 million tons of global packaging plastics that we produce per year to bioplastics would be estimated to require 54% of the current corn production and more than 60% of Europe's annual freshwater withdrawal, which is, a staggering amount of stuff.
And here comes, like, if we need more land to cultivate these plants, then deforestation comes up, right? Or deforestation.
For sure.
Which is another huge issue and can lead to more CO2 in the atmosphere because we take away one of the most important things that we have against CO2, so to say.
Totally.
So it's a delicate balance.
It's absolutely a delicate balance. And I think that's a big part of why Made of Air directly targets waste products.
Yeah.
So a really good, easy source of biomass that doesn't necessarily displace agricultural or cause problems with rainforests is biomass waste. And we generate an unbelievably large amount of biomass waste through all sorts of things, through furniture production, through food. And that resource generally is incinerated or left to degrade.
Yeah.
Both of those things cause the return of the carbon that's stored within that material to the atmosphere. So if you can generate materials from that biomass waste, then it's a very nice and elegant way to sequester carbon.
Yeah. But I guess here we a little bit touch upon another issue of scales. And we see that we have a lot of promising materials, but it's very hard to see how some of those solutions can work at scale, right?
Yep.
So they are good, they might replace a certain amount, but I feel like that a lot of these solutions cannot reach the scale of fossil with being really sustainable.
Which is kind of why there's always this drive for efficiency, which kind of is how I'm going to segue onto the next thing, which is that with our materials in general, we're constantly looking for ways to be more efficient, to reduce our reliance on the raw materials that are required to produce them, and to innovate in ways that saves us all kinds of things.
So what I hear now is that, again, this topic is way more complicated than it seems. And some things that look good at first might lead to issues. And I guess this is a very good point to first talk about sustainability and what it really means. And I guess in the last, let's say 2.5 episodes, we always come to the same conclusion. We find something really cool, but it starts to destroy the world. And probably what we learned since the Industrial Revolution is that coal and then later gas and oil was really cool and helped us develop a lot. But we reached the point when we just can't use it anymore. And what I hear is the corn or sugarcane examples. They seem really cool, but if we overdo it, we destroy farmlands and we do deforestation. They are not going to solve our problem. They might work for 50 years, but they are going to lead to huge issues in like 100 years. Sustainability and what sustainability should mean that we find solutions that are working on a very long time scale, right? What we have to do is not finding one silver bullet that solves all our issues, but we have to get smarter with the materials and find use cases and materials for that.
Yeah, totally. And I think, a great way to go there is to just sort of try and push towards materials that allow adaptability and allow versatility. And I know we've talked a lot about plastics being very versatile and multifunctional, but maybe we have to think simpler in a way. Mm-hmm. And I think there's some fantastic natural examples of how we can be smarter with material design. And the one I'd really like to highlight is composite materials and the way nature and humanity on some level has used composite materials to really provide a sort of adaptive platform that can serve a lot of different purposes. For example, in nature, a great example is bone or shells, which are all examples really of mineralized tissue. And in generally speaking, in composites and in mineralized tissue, what you have is you have something hard. So something that's sort of strong in the broadest possible sense, but often brittle. Mm-hmm. And then you combine that potentially very strong brittle thing with something that sticks it together, or a matrix that can provide a level of additional structural support. So in mineralized tissue like bone, what you have is sort of these often calcium carbonate type materials, and then combined with sort of proteins. So these almost like polymeric things that are tying the whole thing together. Mm-hmm. And what you end up with is something that has the best of both, or excels really in different applications, and how you can regulate the performance of both things together by varying the amounts of them in a wonderful way. There's also obviously examples of this in human man-made materials. A good example is, say, mud brick, which you've probably heard of.
From you, yes, 2 weeks ago.
Okay, well, mud brick dates back to about 4000 BC.
I was very late to this game, I guess.
Very late, right? Get wise.
Yeah.
So mud brick has been used for thousands of years, where people were using a combination of mud with rice husk or straw. And that's a really maybe the earliest composite material. I'm not entirely sure. We might have to check that. But a very fantastic early example of a composite material where you combine these two things to provide something that's much better than both, or that provides a very efficient way to utilize them both. My favorite example...
The seashells are coming.
So my favorite example in general of maybe a composite material, but also certainly of biomineralization, is there are these organisms called coccolithophores. I don't know if you've heard of them.
Yes, from you 2 weeks ago.
So coccolithophores are single-celled organisms which are part of phytoplankton. So they're plankton, right?
Yeah.
You know plankton?
I know plankton.
You know plankton.
I've heard of plankton, yeah.
So they form a group of about 200 species. And what's wonderful about them, or super cool about them, is that they are the most productive calcifying organisms on the planet. So what coccolithophores do is that they cover themselves in these in this calcium carbonate shell called a cocosphere.
This is like full Doctor Who episode.
I mean, cocosphere is just a great word in general. Yeah. The reason they do that is not completely well known, but a prominent theory is that they basically make the shell to increase their durability to resist attack from other forms of ocean-based organism. Mm-hmm. Now, what's really cool about them is that through the formation of this calcium carbonate shell, they take a lot of CO2. So they take a lot of gaseous CO2 dissolved in the ocean, and they use it to form this solid, hard material that forms this protective layer around them. And what's super cool is that when they die, coccolithophores, they sink and they fall to the bottom of the ocean, and then their bodies or their remains, their shells, form a very important and useful permanent storage mechanism for atmospheric carbon. Mm-hmm. And I really love this analogy, not just because of where we work, but in general, or the idea that we can take CO2 out of the atmosphere, we can use it for something, we can form a protective shell, whether it's a panel on a building or the outside of an organism that protects it from attack. And through that process, we can also accomplish this much broader global strategic aim, which is to sequester CO2 from the atmosphere in a way that minimizes or prevents climate change.
What I feel that what we do and a lot of other companies are trying to do is basically take natural resources and use it to some point and improve upon it. And I have this word in my mind, the biomimicry, which we used to do a lot. Yeah, totally. We used to learn from nature and take shapes of birds, and Velcro is coming from plants too, the main idea. And I guess now we are at a point where biomaterials meet science, and we also start to improve upon stuff and change things.
Yes. I mean, I'm very personally fascinated, and a lot of our research at Made of Air revolves around how we can utilize biomass-based materials, but also composite materials to find an efficient and productive thing that serves humanity in terms of climate change, but also is right for a specific application, that it has some sort of value in the application it's intended for. And we play around a lot with things very similar to coccolithophores in terms of this combination of a sort of hard functional unit with a matrix that holds everything together, and that the combination of those two things has some higher value or efficiency gain.
What I hear you saying is we are doing a lot of bio-based or bio-derived things, and we are trying to combine bio-derived materials to come up with 100% bio-derived composites, because that's what we learn from nature. But you also mentioned, and I think that's a really important point, that this material fits a use case or is really good at one thing. So we really have to keep in mind what we are using our materials for and optimize for that.
Yes, completely. So in our research, we very much try and utilize those untapped resources that come in the form of waste biomass, where we can be confident that through their generation or their production, atmospheric carbon has been taken and stored as a solid in some way. And really our challenge at Made of Air is to find ways to turn that process into something beneficial in other applications and to produce materials that are better for the world.
Yeah! That's what we focus on. And why we talk about ourselves is that this is what we know the best, right? We know what we do, but we also see other companies are doing the same. And most of the successful companies that we see are very focused on certain use cases. Some of them are using crops more than we do. Some of them don't focus on the carbon capture part as much as we do, but biodegradability. I think one thing that is common in all the materials that are coming up these days is they are very science heavy or research heavy, but also I think more and more companies, us included, try to use bio-based things much better and much broadly than before.
Yeah, for sure. I think that's it. I think we need innovation that is very clear around our materials and our materials usage. And I think I believe, and I hope I display through my research, that we can solve problems. We can solve some of humanity's greatest problems by innovating, creating new materials and doing cool things.
Yeah, I guess like there is a way to sustainability. The only thing is, as you said, it needs work, it needs a lot of research, and then we can have a pretty nice word that doesn't go to I will edit that part out.
Pretty cool time.
There is a way out. We just need to fundamentally change the things and how we think about them.
Yeah. For sure.
But I guess it happened a few times during
the world.
Yeah. So not hopeless. And thank you for being with us in this crazy roller coaster, nerdy journey of sustainability and learning about coccolithophores.
Coccolithophores. Thanks for listening.
Bye.
Bye.